Hello everyone, welcome to today's quantum spacetime seminar. We are very happy to have Justin David from IISc who will tell us about entanglement entropy of gravitational edge modes. Justin, over to you.
Okay, so there is this, okay, make it smaller. Yeah, so I'll be talking about this topic of entanglement entropy of gravitational edge modes. And this is based on basically the last paper. And okay, there are some inputs from these earlier papers. So it's with Jyotirmoy, who's a student with me at IISc. Okay. So let me begin with an introduction. So of course, everybody in the audience must be knowing entanglement entropy is quite a difficult quantity to evaluate in quantum field theory, and very few exact results are known. And evaluating it for theories with gauge symmetry, even if they are free, right, they have been difficult. As you will see, I mean, we'll see some subtle issues which come up when we think about gauge theories with gauge symmetry. And the usual method has been the replica trick, which is successful in 2D quantum field, 2D CFTs. So it's more successful there. And of course, everybody in the audience knows that we have, it has played a very important role in understanding holography and black hole physics. Okay. And there has been, I mean, if you look at the literature, there has been very little study of entanglement entropy of gravitons. Though it's sort of holographically they're sort of important and so on, as you will see. So very little study, and in fact, one needs, in principle, one needs the entanglement entropy of gravitons if one is interested in a formula like this, which is the generalized entropy. This is, you can think of this as the area of the codimension 2 Ryu-Takanagi's surface, and this is the corrections which are corrections of the bulk entanglement. So in fact, this includes in fact, you have to divide that manifold you have by the Ryu-Takanagi's surface, and you have to evaluate the entanglement entropy across that. Across the bulk, actually, across that two regions. So in principle, this includes entanglement entropy of gravitons across the surface. So similar formula, as you would know, that many of you would know, that played important roles in understanding the information paradox recently. But I would think this, I would be more sort of conservative in saying that, just understanding the Ryu-Takanagi formula with this correction would need, for instance, entanglement entropy of gravitons in principle.
Justin, so first of a couple of things.
Yeah.
So this S bulk is subleading in n counting.
Yeah, it's subleading in n counting. Yeah, that's true. Yeah.
Yeah, and the other thing is that since these are gravitons sort of propagating in a fixed background, the usual the subtleties about entanglement entropy of gauge theories, do they enter here, or
yeah, they should enter. I mean, in principle, they should enter. I mean, here, because it is a fixed background, certainly. But I'm thinking it in a very, sort of conservative sense. In fact, the entangling surface is hugging the boundary. So you think of a holographic setup, and the entangling surface is hugging the boundary, and we are evaluating entanglement across these two subregions. And these corrections are important, and in fact, I think there are papers which compute these corrections to match with the CFT answers. So they are sort of important, but I think gravitons haven't been addressed in this so far as I know. But they would be, just to go ahead, they would be important. For instance, if you look at certain, say, take primaries in the CFT and take descendants, and then you are interested in computing entanglement entropy across an interval excited by a descendant. Then the descendants are like dual to stress tensors in the bulk. And, because, you act by, say, Brasero, I'm talking about 2 + 1, say, ADS3. Descendants, to create descendants, you have to sort of think of, acting by L minuses, which are like dual to gravitons. And there they play a role. I mean, I'm not talking about this. I'm saying in principle, they can play a role. And this is one situation in which they would play a role. Such a situation, I think so far it has not been computed. But certainly for even primary excitations, this corrections is important actually to match the CFD. Yeah.
What do you think would be the corresponding bulk duals for all the higher excitations? Apart, say, suppose you take higher excitations above the say the stress tensor.
Yeah, well, yeah. So there are. I mean, you can actually, like, suppose we want to. Let's talk about just vacuum, and we talk about excitations about the vacuum, a descendant of the vacuum, like L-2 acting on it. L-2 is the Virasoro L-2. That means basically it's the state is generated by just the stress tensor acting on the vacuum. And the dual to it is actually, there is a field. I mean, you can actually construct that field. It's basically a graviton, excited graviton in the bulk. You can in principle construct it. It is known, I mean, how to construct it, though you have to dig up some literature to figure out how to construct it. And that would be the dual to this L-2. But the tower, okay, I mean, in principle, by studying this, you can find the full tower. But certainly the L-2 state is known how to do it in the bulk.
So would you expect that it would be a string theory of some sort, which would the bulk theory would be string theory?
Yeah, if you are interested just in the the global descendants, like L-2. L-2 is okay, stress tensor acting on it. And and descendants of that, I mean, like L-n or some. I mean, there is a class which I think you can restrict to the gravity. I mean, but yeah, I think the full Virasoro, I don't know whether we would access just by using just gravity. That I don't know actually. Yeah. So yeah. So let me go ahead. I mean, this is actually taking me a little bit outside. This is just I wanted to motivate the question. I mean, actually. Shall I go ahead? I mean,
yeah, sure.
Yeah. Okay. Okay. So yeah. So these motivations are sufficient actually to study the question of entanglement entropies of theories with gauge symmetry, including gravitons. And after all, I mean, graviton is a fundamental particle, and we would like to understand its entanglement properties. So let's just to review the setup. So we talk about, defining entanglement of a spatial subregion in quantum field theory. And to do that, we divide take a constant time slice, divide the region into two parts, say, A and its complement, A bar. And suppose the Hilbert space factorizes, suppose it naturally factorizes into this form, into a tensor product of this form, HA and HA bar. Then one constructs the reduced density matrix by tracing out the degrees of freedom A bar in the complement. And the entanglement of that region is just this von Neumann formula. Use the von Neumann formula on the reduced density matrix. And that is the entanglement entropy of region A. But if one is dealing with, say, spin systems on a lattice, or scalars or spinners, then certainly the Hilbert space indeed factorizes and the trace over A bar can be carried out. But if you have theories with gauge symmetries, including that of gravity, they do not admit such a simple factorization as I think people, I don't know if some people, I mean, people have thought about it, several people have thought about it, including Sandeep, and I will relate to his work soon. So certainly it doesn't admit some simple factorization. And what we will see right now is, let me review the situation for Maxwell's theory, and I will sort of give an approach which we developed, which is suitable for extending it to the graviton. Just to understand the issue, it's useful to actually think about Maxwell theory on the lattice. Okay, and so we are looking at a lattice, the spatial lattice. Okay, so that's the lattice we are thinking about. The spatial, the space is discretized into a lattice. Then the basic variables are basically group elements which belong to U1, say, So we are looking at the U1 theory, and they lie on the, I mean, they sit on the links of the lattice. And the gauge invariant observables are Wilson lines, or closed loops of Wilson lines. And so now consider partitioning the lattice into A and A bar. I will give a picture soon. So the Wilson loops, which are gauge invariant operators inside the subregion, cannot change, certain certain elements, the U1 elements, or the electric flux, which emanate, on links on the boundary region. So, for instance, a picture, this picture. Okay, so this is the subregion we are interested in, and if you look at Wilson loop inside, they don't change this flux, which is emanating on these links. Okay, and similarly the other way around. If you look at Wilson loops inside here, they don't change the flux which are emanating inside here. And so the gauge invariant Hilbert space, say we are building it up by products of Wilson loops, Wilson lines, and Wilson loops actually here. So they're Wilson loops, products of Wilson loops lying inside and vice versa. So we build up these Hilbert spaces. But these Hilbert spaces, if you take about the Hilbert space, say the inside Hilbert space, since it cannot affect that links which are out, which are coming out, then we see that given a particular configuration of these electric flux, there is one particular Hilbert space and so on. So the Hilbert space actually decomposes into sectors, and each of the sectors are labeled by the configuration of flux which is coming out. Okay. And so that's what I meant. The sectors are labeled by these electric flux lines or links which are coming out. And the gauge invariant operators, one has either inside or outside, cannot change this flux as we just saw. And the Gauss law, so this is the crucial point. The Gauss law links the inside and the outside Hilbert spaces. The electric flux which are emanating from or going inside and bound, inside and outside, they have to agree. And this Gauss law actually prevents the factorization of the Hilbert space. So let's make it a little bit more explicit. So, so we choose a gauge, say A0 equals 0. Then the gauge invariant states have to satisfy the Gauss law constraint of this form. So therefore, if you sort of take the Gaussian pillbox around that surface, which we are looking at, the normal fields have to agree. The normal component of the electric field outside and inside, they have to agree, right? So the Hilbert space is anyway labeled by these configurations, and the outside and the inside Hilbert spaces are now linked together by this by the Gauss law. Okay. Okay. So the Gauss law links the Hilbert space outside and inside, and thus by choosing a region, just by choosing the region, the gauge invariant Hilbert space decomposes into sectors, and each sector is labeled by the electric field configuration. I mean, the full configuration, a given configuration on the boundary labels a particular sector. So the Hilbert space actually sort of factorizes like this, I mean, as a sum, where each of these spaces are labeled by that electric field inside and outside. So this is not that tensor product decomposition, but a decomposition of this kind. Okay. So that's the sort of crucial difference because of the Gauss law. Okay, and now we look at this particular sort of sum of all these Hilbert spaces of this kind and try to define entanglement entropy. So consider a density matrix in a given sector. So suppose we just take a particular sector. A particular sector is easy to handle. So it's of this kind. This is the wave function outside, wave function inside, and they're all connected by this electric field E. So this is just that we are in this particular subsector. And we can take this and we can, of course, then define the reduced density matrix and go ahead and define the entanglement entropy. Now, but the full density matrix is actually a configuration of this kind. Okay. So where there is some coefficients which indicate the probability that the electric field configuration is of that particular E, and the wave functions, which are factorized wave functions. So this is sort of the form of the density matrix because of the Hilbert spaces of that kind. And then when you perform partial trace on this particular form of the Hilbert space, okay, so we reduce it. So we take the partial trace in each of the sectors and then evaluate the von Neumann entropy using this particular form. We get this formula. So this formula, I mean, because it is essentially comes from this PE rho AE, you just go through the von Neumann formula, and you do get this particular formula. And so there is this configuration, this particular extra term which comes around, and this term is what is known as the entanglement entropy of the edge modes, and it is basically the entropy of the superselection sectors themselves. And then there is this usual sort of the bulk term, as they call it. So this is the usual term. Now, I will talk about both the terms, but our focus will be on evaluating this, this term. Okay. So this second term is usually what is known as the entanglement entropy across the region, and this is in addition to it, okay, because of the fact that there are superselection sectors. So this is what we will sort of evaluate now. Actually. So, and let me just, before I go ahead, and let me just state the result. Okay, some of the results are known, and I will connect it to the known literature soon. So evaluating the, contribution of the edge modes for an entanglement entropy of a spatial sphere. So our regions will be spatial spheres of a U1 theory in arbitrary even dimensions. Okay. So the logarithmic coefficient is what we will be focusing on. So in these even dimensions, entanglement entropy admits a log coefficient of the log, and that's what we will focus on. And we observe that the coefficient of the logarithmic divergence agrees what is known from what is called the edge Harish-Chandra character, which is a different, I mean, at least on the face of it, it's a different object. So we will observe this of the partition function of the U1 theory on a SD, I mean a sphere of D. Okay, so we are looking at entanglement entropy of a spatial even dimension, D dimensions. That means, we take away the time and then we look at a, SD minus 2 sphere, roughly speaking, right? So that is the sphere, spherical entangling surface on the time slice. But somehow that edge modes agree with this particular thing called the edge Harish-Chandra character. I will sort of define all these things a little later.
I have a question.
Yeah.
So this entanglement entropy itself is logarithmically divergent, and then you take the coefficient and then say
there are two contributions. So there is a logarithmic divergence here as well as the logarithmic divergence here. So there are two logarithmic coefficients. Yeah.
So do they cancel each other out or something?
No, they add. We'll see. Actually, they add, and yeah, there is. Yeah. So okay, so this is what we will sort of see. So this is the for the U1 theory, and similarly we'll repeat this computation for the graviton in 4 dimensions. And here too we'll observe that the coefficient of these logarithmic divergence agrees with this Harish-Chandra character of the spin 2 partition function on S4. So all this, I guess, I'll have to define as we go along, actually. Okay, so let's look at the U1 theory first. And of course, the U1 theory in 4 dimensions have been studied quite extensively. In fact, I don't know whether Sandeep is there in the audience, but Sandeep and Sony, I think, have studied it earlier. And there has been other authors, but let me look at it in our way, and then I'll connect it to the approach, to their approach. So this is the formula, right? We are interested in the edge modes, and this is the radial field, electric field configuration on that entangling surface. For us, it's a sphere. And yeah, so that's sort of what I said here. So it's basically this electric field configuration. So what we need is, of course, we need to know what is PE, right? To compute this, we need, given a particular electric field configuration on a radius R, what is the probability that it occurs? And since the theory is free, right? Since the U1 theory is free, and we imagine finding its probability P of E, so it should be a Gaussian. I mean, the probability that this electric configuration is distributed should be a Gaussian, and by just evaluating its moments, we can fix the Gaussian actually. And so the Gaussian should be such that whose standard deviation, is basically the 2-point function of the electric field on the sphere. So let me write that formula. So here it is. This is the Gaussian distributed electric field. And if you take, for instance, the 2-point function, we get basically this GRR, which is the 2-point functions, the radial 2-point function on the, electric field 2-point function on the sphere of radius r. Here is the definition. And n is the normalization, which sort of normalizes this Gaussian probability. Okay.
So I have a question.
Yes.
So when you're choosing this particular P of ER,
right,
what exactly are you kind of basing your choice on? I mean,
so we imagine that P of ER is distributed in some probability distribution, and then imagine evaluating the moments.
Okay.
Right? Imagine evaluating the moments to fix the probability distribution. So imagine evaluating the moments, and then the theory is free, right? So therefore, the 2-point function should fix the moments completely. So therefore, I mean, that's the 2-point function.
Moments of what? Moments of the electric field distribution.
Electric field distributions, yeah.
Okay.
So moments of the probability of the electric field distribution, yeah. So that will fix this configuration. So that is the P of V, and then substituting.
Just a quick question.
Yes.
The choice of which state you're evaluating the entanglement entropy for, is that data inside the correlation function?
So vacuum, yeah. So we are evaluating on the vacuum.
Right, but suppose I wanted to evaluate it in a different state, then would I just look at the 2-point function in that state?
Yeah, I would suppose so. I mean, I would think so. I haven't thought about it actually. Yeah, that's what I would think one would do actually.
Okay, got it. Thank you.
Yeah.
But in general, are you considering the vacuum? Because I thought you had some psi out, psi in bracket, right? So that psi out, psi in is not in general the vacuum, right?
Yeah, they are excited. I mean, it's not like, okay, so the vacuum is like we take the vacuum, and of course the vacuum is some wave function, right? It's a wave function. The vacuum is a wave function, and then we trace out the configurations outside. So that's the way the entanglement is defined. Usually the entanglement entropy is defined on the vacuum. I mean, that's the standard formula. Of course, we can define it on excited state, but the vacuum is some complicated, some horrible wave function. I mean, not horrible. I mean, you can write down for certain states, of course, the wave function, and then you trace out the rest of the outside degrees of freedom, and that's how we define the entanglement entropy. So to create
in general, when you have a certain set of a certain configuration of electric fields inside and outside.
Yes, yeah.
Would you suppose that the state is still in the vacuum state, the state inside and outside?
Yeah, the state is in the vacuum in the sense that they are all, I don't know how to say. So maybe, let me see how, So let's talk about, I think maybe you will understand it in this manner. If I say, take for instance, the, free scalar field, and then look at its ground state. Okay. The ground state, for instance, is actually some sort of a Gaussian, right? It's the ground state is a Gaussian in which we sort of, basically we have, but it's a coupled Gaussian. The Gaussian is sort of connected, delocalized Gaussian. And then we choose out a region, and then we, trace away the rest. But it's a Gaussian in the sense that there is some excitation. I mean, that's what I meant. It's a Gaussian. The vacuum is in fact a Gaussian. Like the harmonic oscillator, for instance, the thing is a Gaussian. And if you take two coupled oscillators and you try to trace out one, you would have this sort of feature, actually. So it's a Gaussian, but it is it's distributed in space.
In general, when you have a certain field, suppose you have a certain just the E. Now, that E is like a creation operator acting on the vacuum, right?
Yes.
I mean, in general.
In general.
Now I would suppose that would make the state.
I'm not particularly sure. Actually, we are not. Of course, that would excite the state, but the calculation we are doing is actually excitations about the vacuum. I mean, in the sense, it's just the vacuum, the entanglement entropy of the vacuum. Yeah, that would change the state, but that would be a different calculation. For instance, you have the state at a particular point, and then there is a new wave function. It's not the Gaussian anymore. It's a new wave function.
I suppose
new wave function, and then you do the reduced density matrix.
But I suppose you are doing it in the first approximation, so excitations are minimal or something, or assuming like that.
Yeah, well, okay. Let me just go ahead and you'll see maybe. Yeah, okay. So if you just substitute this P of E inside this formula, inside the formula of this, and go ahead and evaluate, the summation of integral of P of E, log P of E, P of E log P of E. And if you keep track of just the log coefficient, so the important thing is to keep track of the log coefficient. There are many things which go as area and so on. We're not interested in that. And if you just keep track of the log coefficient, what you get is this thing. It is essentially the determinant of this 2-point function. Okay, think of the 2-point functions as an operator in x and x prime. It's in fact just the determinant of this 2-point function. So of course, this involves a slight amount of calculation, but I think anybody who dealing with free field theories can do this calculation. Just put it inside, and you will convince yourself that it is actually the logarithm term is actually in this. So then the strategy is clear. So we quantize the theory, evaluate this correlator, and obtain its determinant, and extract this logarithmic coefficient. So the strategy is sort of clear. So the technical part is basically evaluating this 2-point function and obtaining its determinant, right? So the symmetry of the problem, in fact, suggests that we quantize it, the Maxwell theory, in spherical vector harmonics, actually. So we quantize the theory in this particular thing. And this is where we differ from Sandeep and Soni, and I will connect it soon. Actually, they are the ones who set up the sort of this approach, this direct approach of evaluating P of E. But I think there are other approaches in the literature which is not as direct, but this is the most direct approach I've seen. But they calculated this electric field correlator slightly differently. So we have a technical simplification for that. And I will connect it soon with their work. So this symmetry of the problem actually suggests that we quantize the Maxwell theory in the spherical vector harmonics. And we expand this mu in basically spherical vector harmonics. You see, this is the time component, which is basically scalar harmonics. This is the radial component, which is still the scalar harmonic. And here there are these two vector harmonics, the gradient of, sort of a gradient kind of gradient of the scalar harmonics here. And this is something which is orthogonal to that. So we expand the, mu, the gauge field in, these harmonics. And you see, this is the gradient. And these harmonics are defined like this. Of course, everybody knows these harmonics. This is certain for some normalization. And there are directions. This is the time component, the radial component. This is that gradient part, and this is orthogonal. And just for future purposes, projections are defined like this. Okay. And so we choose a gauge in which this gradient part, AE, is set to 0. Okay. And then there is a constraint by which we can eliminate A0. And after doing this, after gauge fixing it, we have these degrees of freedom, the AR and its conjugate, and AM and its momentum conjugate. Let me just sort of see that. So we have, so we have these fields. This and these are the ones which we keep, and these are the gauge fixed. This is easy to see it's gauge fixed because it's gradient of the scalar harmonics themselves, and therefore you see the gauge transformation transforms like the gradient, and therefore you can choose that to kill this AE. And there is a constraint which sort of which is used to eliminate the A naught. So you can choose that gauge, and these are the degrees of freedom after that. And if you can solve the equations. You can solve the equations of motion, the radial wave equations. In fact, for instance, here is this radial wave equations. Even pi r has the some wave equations which you can solve, and you can expand the AR and pi r, for instance, in terms of the Bessel functions. In fact, spherical Bessel functions. And the creation annihilation operators associated with it. This is similar to the plane wave expansion, except that we are keeping the spherical symmetry intact, and we are expanding it in modes spherical waves, essentially. And these are, the creation annihilation operators for the spherical waves. And in fact, so that can be seen by the canonical commutation relations. Okay. And so we have canonically quantized this gauge freedom, and these are the this commutation relations imply these commutation relations, so we have basically quantized these gauge fields.
The pi r are just the radial electric fields, right? The pi r.
That's right. Yeah. Good. I didn't say it. Yeah, pi r is just. You will see a formula later. Yeah, pi r is just the radial electric field. Yes. In fact, that's what we are going to focus on soon. Yeah, that's true. So therefore, in fact, the electric field is related to the pi r. If you look at all the reality conditions and so on, it's pi r star, and that's the electric field operator. And therefore, substituting, since we have already written it in terms of modes, you can just substitute it and evaluate the the 2-point function of interest. It will lead you to do this particular integral. It comes out in spherical wave decomposition. The theta and phi r, that is the natural, that's the sort of interesting part of it. It comes out in the nice spherical wave decomposition. You have to do this integral. And you can see that, TR essentially is scalar in terms of the sphere. In terms of the sphere, it's a scalar. And that's the reason YLM comes. Only the scalar harmonic comes in this. So we basically have the 2-point function. We need to do the integral. Now this integral can be done. There's a formula in the literature which gives you the formula for this integral. And this is, okay, you can write it in terms of hypergeometric function also. It's a particular function. I will tell you the properties we need of this function. It's a particular Legendre function. So we get the 2-point function. So these are on separated spheres, right? R and R prime. We need to, take R equals R prime. So this was the advantage. I mean, we can write down the correlator nicely, and it just comes out in terms of its spherical wave decomposition. Okay. And now, so the 2-point function is this, and it's diagonal in the LM basis because of the fact it is just YLM times YLM star. It's actually diagonal. That operator is diagonal. And one more thing is that this function, this Legendre function of the second kind, what we need is that when you take the coincident limit, there is a divergence, but it doesn't matter. What is important is that it is independent of L. Okay, this limit R goes to R prime is independent of L. So therefore, all the L dependence, so this operator is diagonal, and all the L dependence in the coincident, when you look at the correlator on the sphere, is basically sitting here, L into L plus 1. Okay, so therefore the diagonal entries of the 2-point function of the sphere are proportional to the eigenvalues of the Laplacian on the sphere. So that's sort of result. The diagonal entries are proportional to these eigenvalues of the Laplacian of the scalar, of a scalar on S2. Okay. And evaluating the entanglement entropy essentially, we need to just take the partition function or one loop partition function of the scalar on the sphere. So it's basically determinant of that operator, which is 2L into, this is the degeneracy, and this is the eigenvalues. So determinant of this operator. And this, so the logarithmic coefficient, okay, this right now I'm making this statement, but you will see it in more general soon, is actually.
I have a question.
Yes.
So when you are saying that it's diagonal in L and M,
yeah.
Are you assuming a specific sort of profile for the theta phi dependence?
No, theta phi comes out from the calculation as YLM, the same YLM star.
Yeah, but for a generic sort of theta phi profile, I would presume that you would have some dependence on the L and M also. It wouldn't be diagonal. I mean, when you convert to Fourier basis from the theta phi to L and M, I would presume that you would have some dependence on the L and M, because if it has some non-trivial dependence on the theta phi, when you Fourier transform it, in general, it can't be just be diagonal, right?
Right, but yeah, so we take, so let me tell you so we take this FTR, which is basically an expansion in YLM, right? And there is basically a LM and its coefficients. And then we just compute this because pi is basically this. Okay, pi RT is this. So we just compute its 2-point function. Okay, and we use the creation annihilation operator, a dagger operator on the vacuum. So yeah, so we just calculate it and this comes out. Because this creation annihilation operators are diagonal. L and LL prime. That's how it's forced actually. These operators are mode by mode basically, and that feeds into this calculation, and it just becomes the same. Yeah. So there's no assumption. It's just straight calculation actually. Yeah. So that's yeah. So that's the sort of.
Justin, can you hear?
Yeah.
Hi. Sorry, this is Shiraz speaking.
Hi, Shiraz. Hi, Shiraz. Yeah. Go ahead. Go ahead. I can't hear you, Shiraz. I'll increase the volume here. Okay, go ahead.
Can you hear now?
Yeah, now I can hear you.
Excellent. Sorry. So if you evaluated your 2-point function in position space, you could do it just by weak contraction and Cartesian coordinates, right?
Yeah.
So that would be a simple answer. And you're saying if you take that answer and you express that in spherical harmonics, this is what you get.
Yes, yeah, that's what you'll get. Yeah.
Okay.
Yeah. And in fact, Sandeep and Sony, I mean, they did that. Yeah. I will connect it with soon with that. Yeah.
Okay. Yeah. I had one other question, which is sort of general one, which I wanted to ask you at the beginning, but I couldn't get my quote. I just asked, and maybe if this is not the right time, we can talk about it later. But my main memory was that this definition of the entanglement entropy, where you specify, where you work with this electric definition. This is one of many possible definitions.
Right. It's one of the many possible definitions. Yeah, that's true. And we have chosen a particular definition to evaluate the edge mode. You can choose a magnetic version, and in fact, that turns out to be the same. The calculation for the edge mode.
Right. It doesn't matter what choice you make. There's something universal about what you're calculating.
Well, I mean, the electric and the magnetic are related, but I think Cassini would say that there is some complicated, which I haven't understood, the complicated way of choosing these centers such that we don't even have this contribution. But I'm not like, yeah, I don't know. But if you choose the electric center and the magnetic version, magnetic flux, if you choose that, yeah, certainly. I mean, then the answer is the same.
And is there something special about this definition? I mean, is it singled out naturally, for instance, by the replica trick or something like that?
Okay, I'll connect it with the replica trick thing, and I will connect it with the partition function on the sphere. Actually, I think the partition functions on spheres actually single out these things. I will okay, I'll get to that stage soon. Yeah.
Just one more quick question.
Yeah.
I mean, since if you have a conformally invariant theory, then a sphere is conformally equivalent to a half cut, right? Half space cut.
Yeah, that's
so
correct.
So could I have like reproduced this result just by looking at a half space cut instead of a sphere?
Yeah. I mean, I think we miss out the edge modes when we do that. I mean, because that becomes something, the hyperbolic cylinder, because the boundary conditions naturally are like zero, like there. I mean, somehow the boundary it is not sensitive to the boundary condition, but maybe there is a way of keeping. I will connect with that also. Maybe there's a way of keeping track of the boundary conditions there, and doing it more precisely. But
I mean, in a sense, I was wondering whether the contribution you're computing is somehow related to the conformal anomaly going between, like a half space cut to a spherical cut. But okay,
no, it's all right. I will connect. Let me just
okay, great. Thank you.
Deal with all that. I will talk about. So so it's convenient, and then we have this particular formula. And essentially, so we just need to look at the logarithmic divergence of this partition function of a scalar on S2. Okay. And okay, so here it's, I mean, there are many ways of getting this, but I'm writing this in anticipation with something. So we rewrite the free energy of this scalar on S2 in a particular way. It's basically a heat kernel way of writing it. But when we write it like this, this has an independent meaning of a character, something, and which I will define, which I will sort of at least talk about a little bit later. So you can write it like this, and the logarithmic divergence is basically the 1/t coefficient of this. Okay, I will actually elaborate on this a little bit later. So the logarithmic divergence is basically 1/t. So there's a very nice way of writing this partition function using a set of identities. Which was actually...
Sorry, I have a question.
Yes.
When you say that the logarithmic divergence is the coefficient of the 1/t, do you include the dt? Do you include the t in the dt over 2t, or do you exclude it?
Yeah, dt is just separate. The integrand, the 1/t in the integrand. Yeah, in the integrand.
Okay, so okay, so the logarithmic divergence is just the part in the 1 plus e to the minus t by 1 minus e to the minus t times the rest of it, right?
Yeah.
That's the coefficient of the 1/t.
1/t, yeah. So you expand that, you expand it, this times this, you expand it and extract out the 1/t. Yeah.
Okay.
Yeah. So this is, of course, I mean, it's a little technical, but it's basically just a set of identities which make this partition function look like this. And I will indicate this soon. And so extracting this coefficient from here, you get 1/3, which is what has been evaluated for this edge modes in 4 dimensions. And let me now connect with, so the earlier work. So the evaluation of these edge modes have been carried out by several groups. And in fact, our method is a modified method of Soni and Trivedi's method, where they worked, we worked directly in polar coordinates using spherical harmonics. And what they did was they worked in the Coulomb gauge, evaluated the position space in Cartesian coordinates. In fact, it was evaluated in Cartesian coordinates. The quantization was done in Cartesian coordinates. And they converted the result to polar coordinates and then finally performed the spherical wave decomposition. So that's how they worked in. And in fact, this is their answer. If you look at their paper, it's a result in their paper. This is their answer. And, this is that bilinear of the YLMs and so on. And we have actually compared our answer in the compact Legendre polynomial form, Legendre function form, and it agrees. We just perform an expansion in alpha. And the two series agree. We haven't actually shown the set of identities which relate them, but we just compared them in Mathematica, and they precisely agree. Okay, so they did it differently, but this method has an efficiency in the sense that directly we get the thing in the spherical basis. Now, let me connect with the other things, right? We have seen the entanglement entropy gauge field is given by this. So there's an edge, S edge and S bulk. Now, the coefficients are, the logarithmic term is 1/3. And then this is known, actually, 16 by 45. is known by a couple of methods, maybe even more. So here, originally that was evaluated by Cassini and Huerta. And actually what they do was they take this, the U1 theory, do the spherical wave decomposition and so on. And they map it to, scalars, two scalars without the L equals 0 mode. And from there they extract, by the fact that they are related to scalars, they extract the log coefficient. There's another way, which is related to these maps, which Onka was talking about, using the hyperbolic cylinder partition function. Like there is a map to something called the hyperbolic cylinder, basically ADS3 cross the S1. So using that particular map, also we can evaluate this particular term. And in fact, that is insensitive. And that also gives just this part, the bulk part. Now, if you combine both of them, that is the anomaly, the Euler A-type anomaly. If you combine both of these things, it's the anomaly. And if you use, I think, the replica trick directly, you get this. You get 31 by 45. You get this coefficient, actually. So, in fact, ADS-CFT also gives the combined coefficient. So which is, but okay, people in information theory says that, in fact, this 1/3 is just an entanglement of various sectors, various sectors the theory can be in. So it's only the bulk term which measures the true entanglement of the theory of the vacuum. So people, they have conflicting views, but this is the observation. So this coefficient is 1/3, and this is the other coefficient. Together they make the Euler A-type anomaly coefficient. Okay. And now, using this approach, actually, since we have developed this, quantization in these vector harmonics and so on, you can actually generalize this calculation to arbitrary even dimensions.
Justin, just yes. So I understand, quick question. If I did the calculation for a half space cut, would I get the same 31 over 45?
Yeah, if the half space cut is related to this, this hyperbolic cylinder, which I feel it should be, then I think you would get this one, 16 by 45. Okay, I think that is half space thing is something like, it is conformally related to the hyperbolic cylinder. That's how this Cassini-Huerta map works. And that gives you actually 16 by 45. So surprisingly, actually, that was the puzzle. Actually, that was a puzzle for some time. Actually, somehow that gives this. But that's somehow if you see that map, it sets the gauge field on the boundary to 0. On the the boundary, which is basically the entangling surface. The entangling surface gets mapped to the boundary of the hyperbolic cylinder, and sets it to 0. Yeah,
I see.
But in the half space thing, then you're not setting the electric field to 0.
Sorry?
In the half space thing,
then
you're not setting this field to 0, right?
Yeah, if you're Yeah, I can say for the hyperbolic cylinder, certainly it's set to 0, but maybe in this half space calculation one is not. Well, then,
because it looks like you're doing the same thing on the sphere. Just or not?
So there is from the half space there is a further map to the hyperbolic cylinder. So maybe if you're just in the half space, maybe one has to keep track of the gauge field at the boundary, and I don't know actually whether anybody has done it directly like that.
It sounds to me that if the difference between the hyperbolic thing and what you're getting is that the freezing of the electric field.
That's correct actually.
Then it sounds to me that the half space is more like what you have than the hyperbolic.
Right. Okay. Yeah, and also I was thinking the half space is conformally equivalent to the spherical cut, right? So I was thinking that you should get the same answer.
Even the hyperbolic cylinder is equal, actually. Is conformally equivalent.
But you're saying that the boundary conditions.
Yeah, it's a boundary conditions. Yeah, it's a boundary.
However, in the half space sphere, the boundary conditions don't change.
Okay. I don't know anybody has done it directly. Maybe most likely it will come out.
And how exactly do you do the bulk computation? Because I suppose you would have to have duals of the electric field, right? In the bulk.
No. This is just a partition function calculation on the hyperbolic cylinder. Like this calculation is a partition function calculation. This calculation is a mode by mode calculation. Like you take the, you quantize it exactly like the way you do. And then you see that the degrees of freedom are like two scalars without this mode. And then you know that, I mean, people have done the calculation for these scalars. And that's the way this Cassinian, these people did it. And this is just...
Yeah, but I'm asking about the ADS computation. In the ADS space, what do you compute?
Well, this is a different ADS actually. This is not like holographic. It's just somehow this calculation is mapped to partition functions on, the hyperbolic cylinder, meaning there is an ADS3 cross S1. It's not, the field theory itself is on this. It's not there is a bulk dual or anything. So the field theory, though initially we started with flat space with an entangling surface, but using these conformal maps, you can map it to this particular space actually.
How does a dictionary work out then? ADS-CFT dictionary.
There's no, it's not ADS-CFT, I should say. It's just like taking the U1 theory, instead of taking it on a flat space or something or a sphere, we take it on this particular space. Yeah. There is no ADS-CFT here actually. Yeah. It's just the theory on this particular curved space for which we need to evaluate.
But there is a bulk theory and there is a boundary theory, right?
Well, yeah, well, okay, if you're talking about this being the bulk modes, but I don't mean it in terms of ADS-CFT. Yeah.
The ADS would also be a 4-dimensional. Yes.
I can't hear actually. Yeah. Yeah. I can't hear.
Can you hear?
Yeah. Okay. Go ahead.
I was just saying for the question that I think the ADS would be the same dimension as this calculation.
Yeah. That's true. Yeah, actually. Yeah.
So one follow-up question about this hyperboloid.
Yeah.
ADS4, and actually ADS4 is especially nice for this. There are two natural kind of boundary conditions you can put around.
Okay.
Right? There are boundary conditions where you set the non-normalizable modes to 0.
Yeah.
Which are sort of like we just set the electric fields to 0.
Yeah.
And then there are the boundary conditions where you set the normalizable modes to 0.
Right. Yeah.
I was wondering whether the second one might actually bang on give you.
Yeah, I haven't explored that. We've done the other one only actually. Yeah, I haven't done that one. Yeah, I understand. Yeah.
Because that one would allow the electric field to fluctuate.
Yeah.
So,
Yeah.
Okay. Yeah. Thank you.
Okay. This is all discussion. And okay, so what we can do is, people are hearing me, right? I mean, I haven't lost any connection.
Yes, we can hear you.
Yeah. So using this approach, we can generalize this calculation to arbitrary d dimensions actually. Quite simply, basically the vector harmonics. I mean, we sort of generalize it to higher dimensions. And we can calculate the 2-point functions, and as expected, I mean, this coefficient becomes the the scalar Laplacian of a d-2 sphere actually, and one can evaluate the logarithmic coefficient from there and extract out the log coefficient. But let us, I mean, there is a structure to this. Okay. So the free energy of this particular, I mean, it's basically again, so the conclusion is that in higher dimensions, this coefficient, instead of L into L plus 1, it becomes the appropriate Laplacian on the d-2 entangling sphere. So we evaluate this edge modes, I mean, the determinant basically, and we can write it in terms of this, again, this nice integrand. Of this kind, and extract the coefficient of 1 by t is essentially the log divergence. But that particular form is not, and the number is not so crucial rather than the structure. Okay.
I have a question.
Yes.
Instead of electric fields, if you took scalar fields to start with, how would the analysis be any different?
Yeah. So then, I mean, the question, we can calculate this, and the question is whether you want to hold some, particular configuration fixed at the boundary or not. People usually don't, I mean, there is no super selection sectors like that, first place, for the scalar fields. But yeah, maybe there are configurations you can choose to hold fixed and do the calculation. But usually people don't don't choose any particular. I mean, the natural, like this Hilbert space sort of decomposes, and there is no there is this electric field which connects the two Hilbert spaces is no longer there for the scalar field. So such
you could assume that there are some certain scalar degrees of freedom on the boundary, right? Instead of the electric
yeah, you could. Yeah, so there are some there are certain ambiguities in some cases in scalar fields. Yeah, but there are certain ambiguities, and there is some. Maybe let me not go into that actually. In fact, in scalars also there are some choices in which you can make to have these kind of degrees of edge modes there too. Actually,
no. But my question is how is the vector nature of the electric field coming in here? Because all we are seeing is that it's just behaving like a scalar to all practical purposes, right?
Well, that 2-point function, that crucial, the logarithmic coefficient, I mean, there's a lot of things there. Logarithmic coefficient of that 2-point function, which we are interested in, has that particular behavior. So this is the electric field, and somehow, this thing is coming out when we do this calculation. Yeah.
So, for instance, if you had a scalar field instead of an electric field there, instead of FR...
Yeah, one doesn't have anything, actually. Naturally, one doesn't have anything, yeah.
No, if you had boundary degrees of freedom, for instance, instead of the electric field, boundary scalars, so then you would have a similar term, right?
Yeah. One, I mean, I don't know whether you'd have this term. Yeah, it would be different. I don't know. If it depends on your boundary condition. Yeah.
Okay.
So this calculation goes, I mean, yeah, this is the calculation. And okay, let us look at the structure. Okay, this is basically rewriting this, when you calculate this, you write this, you write the log in some representation and do certain manipulations, and you can cast it in this form, where this has a meaning of a character, actually. It has a meaning of a character. So let me just so there is this particular transform. You can think of this as this red part as a transform, and this is a particular form of a character. So what is this character? So this is a character. It's the Harish-Chandra character. So let me just define it. So consider a minimally coupled scalar of mass m in d-2 de Sitter space, right? Okay, d-2 de Sitter space. So this has this isometry, and the Euclidean continuation of this is of course a sphere, d-2 sphere. And define these two numbers, and this is similar to the ADS-CFT, d mass versus delta dimensions, except that here the sign is different. Okay, and the character is Harish-Chandra character is you take this representation, this given delta plus and delta, you take that representation of the particular delta, which is basically an eigenvalue of SO11. And then you consider that representation, and then you take all the traces, the trace over all the states of in that multiplet. I will give a simple example, and this is a formula for that. Actually, this is a formula for a scalar character, basically. And if you put so the trace is taken in this. So let me just to fix this idea. Like suppose we are looking at SU2, okay. And we're looking at the spin J representation, and you basically take the weights, the karta, e to the power 2 pi J3, which is similar to the SO11, which we are interested in, and take the sum over all the representations, all the states of the representation, and then you get a particular formula. So this character is similar to that. Okay. Yeah.
Is this a standard SO d-3,1 character? Character over the states of a minimally coupled scalar field or some
yeah, it is actually.
De Sitter space.
Yeah, de Sitter space. Yeah.
H is just, what is H in that term?
This H is this boost, SO1,1 boost. This is the eigenvalue, it's the Cartan generator, Cartan corresponding to this boost.
Okay. Yeah, so there's this, these unitary representations of de Sitter space are sort of classified. There's this.
Yeah.
This is the exceptional part.
Right.
And this is one of these d/2 plus IU type?
Yeah, correct, indeed. Yeah, I didn't want to go into that. Yeah, it is indeed that representation. Yeah.
Okay,
yeah. So it's that, and so for the massless scalar, in fact, you just plug this formula m equals 0, and you get this result. So that's this partition, the logarithmic coefficient is extracted by this transform of this particular Harish-Chandra character. Now, of course, I mean, this has been, these observations of these for the partition functions rewritten like this was recently made, actually, starting by the work of Denef we have done for certain other fields, actually. But now let us just consider the U1 theory on the full sphere, D sphere. Okay, and in terms of and its partition function, the complete U1 theory on the full sphere. You can write down its partition function exactly using these methods. And then there is a term, which, it decomposes into two. This was the fundamental observation of Denef and all. So it decomposes into two parts, a bulk and an edge. Okay, the bulks are characters, associated with the full D sphere. I mean, they come with a D-2 for a D-1 with the particular weights and so on. But there is an edge part, which is basically the character in the lower, 2 dimensions lower. And you see that D-3 structures coming in. And in fact, if you just look at the partition function of the U1 theory on the full sphere ST, it decomposes into 2 parts. And this, if you just extract out the edge part, it is indeed, the logarithmic coefficient from this part coincides with the explicit calculation of the entanglement entropy of the edge modes. So this is sort of an observation. I mean, deeply, I don't understand the observation. I mean, I don't understand the reason why this, this sort of works. But indeed, there is this, the edge character somehow is essentially the entanglement entropy of those superselection sectors.
Just to understand the dimensions.
Yeah.
If we were in 4 space-time dimensions originally, then your edge modes are like modes that live in de-Sitter 2.
De-Sitter ADS, yeah, 2 dimensions. I mean, let me also just go back. Yeah, so if you are in 4 dimensions, it is 4 minus 2. Yeah, it's Euclidean de-Sitter D-2. Yeah, 4 minus 3. Yeah. So SO 1, 1, yeah, de-Sitter 2, yeah.
Okay, fine. And then that de-Sitter 2 is sort of identified as some analytic continuation of the spatial S2.
S2, yeah. Somehow the characters for S2s are actually de-Sitter characters. That's surprising. I mean, yeah. Because I guess, analytic continuation, it comes from basically the, I think there is this one patch, static patch analytic continuation, yeah.
Right.
Yeah.
Thank you.
Yeah. So this observation. Now, with this, all these things about the U1 theory, we can actually go to I'm at 12. So it's the gravitons. Okay. Now, so we are considering linearized theory. It's very simple. I mean, the most simplified theory we took just it's just flat space gravitons. So this is the action. It admits this gauge symmetry. And the Riemann curvature is the gauge invariant object.
Sorry, Justin, could I just quickly ask one question?
Yeah.
Is there some way to understand this relationship via the replica trick? Because somehow the replica trick would naturally involve a d-dimensional manifold, like an SD, at least topologically an SD, but with some conical deficit.
Yeah, I suppose. I mean, we can actually, I mean, we have seen that, so we have seen that when we take, branch sphere partition functions, meaning, spheres which have the conical defect, right?
Right.
Then also it splits like this, okay? It splits like this, but this, and the branching does not, I mean, the edge modes don't have branching factors. I mean, I have to show you those formulas, but I mean, for like when there is branching, for instance, like the bulk part comes with some factors like Q here and so on. The edge modes don't. But that's the observation we have. But how to translate that observation? I'm not.
I have a related question.
Yes.
So the edge modes, I mean, the edge modes live on the surface of the DS2, right? I mean, they live on DS2, right? The surface of the...
It's a partition, I mean, yeah, the character of the edge modes, I mean, or the contribution, logarithmic coefficients of the edge modes can be extracted from partition functions of the...
Yeah. Now, this...
Bulk, yeah, the bulk of the disk, yeah.
Yeah. So, yeah, I mean...
Two-dimensional disk, yeah.
Yeah, I mean, they're analogous to the sphere that you had previously.
Right.
Yeah. So instead of the surface of the sphere, you have the surface of the DS2. I mean, instead of S2, you have DS2. So
right. I mean, that is this mathematical correspondence for the partition function.
Yeah. Now, I would suppose that the Laplacian on the DS2 would just be the dimensional reduction of the Laplacian on the 4 manifold, right? I mean, in some sense, because you're just restricting to the DS2, which is like the boundary of which separates the two regions. Okay. Isn't that correct?
Yeah.
So in that case, the character of the Laplacian would just be instead of in that formula e to the d minus 2 plus e to the minus t. You would simply have e to the minus d minus 3 plus e to the minus 0, something like that. Because is the characters, the corresponding characters are just dimensionally, I mean, they correspond to the dimensionally reduced Laplacian on the DS2.
Yeah.
Isn't that correct?
Yeah. Yeah. Maybe I can take it later. But let me just go ahead. I don't understand it fully, actually. Yeah, let me just go ahead. Actually, I'll come back. Okay, let's do the gravitons and then we'll come back. Okay. So the Lagrangian admits this gauge symmetry, and this is the gauge invariant quantity. I mean, for this linearized theory, for instance, this remains gauge invariant, and the equations of motion are the Einstein's equation composed out of this curvature. Okay. Now, in the case of the Maxwell, so here is the point actually. So I want to get at this. So in the case of the Maxwell field, the Gauss law resulted in the superselection sectors. Okay. To obtain a gauge invariant characterization of the superselection sectors, we have to think of the Riemann curvature as the field strength of a U1 potential, actually. So that's the best way to get it. Because, I mean, if you think about the Gauss, I mean, the constraints in gravity, okay, it's a certain constraint, but you have to write it as a total divergence or something like that, no, to understand. But then you lose its gauge invariant, you'll see that, you'll lose that gauge invariant kind of characterization. So let us think of the Riemann curvature as a field strength of a U1 gauge potential. So how can we do that? Okay, so consider this gauge potential constructed out of the graviton. We just take the linearized graviton and construct this object. Okay, and under this, you know, this coordinate transformation that h mu nu goes to del mu, epsilon mu, and zeta mu, and a symmetrized version of that. This guy transforms in this very similar. It's similar to the U1 field. It transforms like this. Okay, you can just plug it inside and check it, and so therefore, the Riemann curvature can be rewritten as a field strength of this field, of this U1 gauge field. So it can be rewritten like this. Okay, and so then, so you can think of this basically this R mu nu as the field strength, and these alpha beta as some sort of internal indices. Then the Hamiltonian constraints, which are of these are the Hamiltonian constraints of gravity. Now,
Justin, just a quick question.
Yeah.
Is your connection A just a linearized Christoffel connection? Or?
This one? Yeah, maybe. I didn't check.
Oh, okay.
Yeah, I didn't check. Yeah, maybe it is. Yeah. But yeah, it's just naturally comes. I mean, you can just rewrite this in a very simple way. I didn't
Sure.
Yeah.
Okay, thank you.
Yeah. So,
Yeah,
but in order to be consistent, it has to be.
It probably is, and that is why the Riemann curvature.
Yeah, this is, yeah, it's probably is, yeah.
Yeah, so because it's linearized, the AA terms don't appear. It's just the derivative terms.
Yeah.
And in any case, in order to be consistent, it has to be, because the Riemann tensor has to be the curvature corresponding to the
yeah, the A wedge A kind of term is not there, and this is the first two terms. Yeah, it could be. Yeah, it is. Yeah, most likely that. Yeah. So so the Hamiltonian constraints of gravity is this, and imagine. I mean, this is hard to write this as a total divergence or something and so on. But using the Bianchi identities, one can show that this constraints imply these constraints on the on the conditions on the curvature. These constraints imply this, and therefore these are like the divergence condition on the R, which is interpreted as the U1 kind of U1 field strength. So the curvature components are analogous to the U1 field strength, and these constraints are obtained from the Hamiltonian constraints of the gravity or the Gauss law constraints. So what one needs is the superselection sectors are labeled by these components 0rij and 0r, because basically the radial component, we're taking a sphere and we look at the radial components of these things, and these are there are 6 components. If you count them, there seems to be 6 components. Okay, now let's go ahead with this. So this is the way we are going to proceed, because we are thinking of them as very similar to the U1 theory. We are thinking of it like that, and it seems to be there are these so many constraints.
I have a naive question.
Yes.
Like in the U1 case, you assume that the Wilson loops didn't have any effect on the edge modes, right?
Yeah.
Is that correct?
Right. I mean, that doesn't have any. It doesn't affect those configurations which are coming.
But here, since gravity is self-interacting, I would suppose that.
Well, this is linearized gravity. This is just linear. I mean, the theory doesn't have Newton's constant also. It's just that.
But it's still a non-abelian theory, right?
Well, I mean, this is abelian as far as I know, because I mean, because you want it's a field strength of, I mean, the transformation is of this kind.
But I mean, isn't that trivializing the theory too much if you don't take into account the non-abelian nature of the?
Yeah, it is. Of course, it's a very simplified case, but even the simplified case, one would like to understand. Yeah. Okay. Yeah, indeed, it's very simple. Yeah. So, yeah, that's true. Actually, it's a very simplified case. So, so there are these 6 components, and the strategy to determine the contribution is basically we follow the similar strategy: gauge fix and quantize the theory using the expansion of the metric in terms of its tensor harmonics. Determine the relation of the 6 components of the curvature to the gauge fixed operators used for quantizing the theory. You remember that the pi r was related to the what we wanted, F0, the radial electric field. So, and we can find out from this how many of these are local in radial coordinates. There are 6 of them. We will see actually only 2 are local in this relation, and evaluate the 2-point function of the curvature correlators and extract the log coefficients. So that's the same strategy we follow, because we have like simplified the implementation of the Gauss law constraint in this manner. Now, so the spin-2 field is written in terms of these tensors and vector harmonics and then scalar. So the tensor mode, tensor mode is basically the spatial modes. The vector mode is when one index is spatial and one index is temporal, and so on. So there is this, there are 1 scalar, 3 vectors, and 6 tensor. Each of these modes are expanded in their appropriate harmonics, and one can choose a gauge. So this is actually, this gauge fixing and all was done by these guys. And they did it to find that bulk entanglement. I'll relate to it later. But so these people, they actually took the theory, they expanded it in these modes, and they gauge fixed it. Importantly, they gauge fixed it. And the gauge fixing basically, you can set the scalar, the vector, and 4 of the tensor modes to 0. And there are only 2 tensor modes left behind, which is basically the gauge invariant degrees of freedom in this particular gauge. And it's a long process to fix the gauge actually. But it is important to do it in this, at least to get it to the state we are in. So these are the tensor modes, which we quantize the theory in. There are two particular modes and its conjugate, similar to the electric field. And in fact, one can find the equations of motion for both of these fields. And if you solve the equations of motion, you can again write it in terms of spherical way, Bessel functions, quantize it in this particular way, okay, a similar way. These are the commutation relations, creation and annihilation operators can be found. Now we need to relate these 6 components. So we have quantized the theory, we have gauge fixed and quantized the theory, and we are actually, we have expanded it into on-shell modes. So we need to relate these, these curvature components, which we need to fix at the boundary to the, to these, the variables which are quantizing in, right? And we can indeed, and this was a very tedious calculation, and I think Jyoti Moy did it in Mathematica. So we could relate, so this component is one of the components in the Gauss law actually, RPREM. This could be related directly to this momentum. And there's another one which is also part of the Gauss law, could be related to another of the field. Okay, so 2 of them. The rest, among the 6 Gauss law, putative Gauss law constraints, only 2 of them were local. Okay, and all these are non-local. In fact, it's only the sort of scalar in some sense is local. And the rest of all of them were non-local. You can see there's these things. How many have I written? 1, 2, 3, 4, 5, 6. Yeah, all of the rest are non-local. And the relationship between the curvature components and the operators generating the Hilbert space is local. Generally one uses local algebras, and so we choose these. Among these, we choose only the local ones. We fix only the local ones, and we evaluate. In fact, so these are the relations. The RTREM and RTRT are these 2 are the particular ones which are.
I have a question.
Yes, yeah.
Are you setting G to 0?
G, which G?
Newton's constant.
Yeah, there is no Newton's constant in this. Yeah.
So in that case, A by 4G it would diverge, right?
A by 4G. What is A by?
The first term, the area term in the entanglement entropy.
That is something in the fixed gravitational background. That's a different. Here we are really dealing with a very simplified theory. That was just sort of motivation for calculating the entanglement entropy for gravitons. But here we are really the most simplified theory we could think of, which has a spin-2 field. So we are in a very different setup here, actually. Yeah, it's just almost like field theory. You're treating them, like field theory. So they are related. So there are 2 of them, 2 of these Gauss laws, which are related locally to the operators generating the Hilbert space. And we calculate the 2-point function of those 2, basically. So again, we go through the same process. It's because we have developed that formalism for the U1, it's reasonably simple to calculate the 2-point function. And it sort of becomes this kind. So the operator, is complicated actually. It's a complicated operator, and but it's the same for both. It's the same for both the fields we have to fix using the Gauss law, and we calculate the edge mode contribution by this particular way. By using the same log and writing it in some structure, using heat kernel methods, for instance, to evaluate the log coefficient. And if you do that, you get 16 by 3. Okay. So that's the coefficient we get, 16 by 3. Now let us again look at the observations we had. So compare the coefficient of the linearized graviton to the massless spin-2 field on the full sphere. Okay, so here's the full sphere, And indeed, it decomposes into a bulk and the edge part. And if you extract the coefficient, the log coefficient from the edge now, it coincides with the 16/3, just as for the U1 case. So they agree, this coefficients, the log coefficients using, it was an observation in the U1, and we just try to see if that observation is true for the sphere S4, for the spin 2 field, and indeed it is true. The bulk part has a story by itself. So the bulk part, in fact, was very recently evaluated by these authors. And they actually do these quantization. They use this, quantization in terms of these modes and identify the two scalars. And in that case, there is no 0 and 1. Both the modes have to be removed, and they extract out the log coefficient. We have done it using the hyperbolic cylinder partition function, and both methods agree. 61/45 is what we get. Now, totally, it becomes, if you put them together, there is another coefficient, 301/45. But unfortunately, in this case, we don't have an anomaly or something to compare against, as far as I can think of. But there is a particular coefficient which for the whole bulk and the edge. And
this Hewitt and Cassini calculation, do they assume G Newton to be 0?
Yes, yeah.
Okay.
Yeah, it's for the same theory. This particular, linearized graviton. Yeah. Now, for arbitrary spins.
Just a quick question.
Yeah.
I sometimes hear people saying that divergences in entanglement entropy in gravity are cancelled, are tightly related to divergences in Newton's constant. And in fact, you can absorb one into the other.
Okay.
So that if you think of something like A/4G plus this one loop piece, if you include both the divergence in Newton's constant and the entanglement entropy, these two were cancelled.
Okay.
Do you know if this is true?
I don't know. We are just calculating this S bulk kind of thing, right? So
right.
I don't know whether, so together, whether they will cancel with something in the A/4G. A good test, I've been thinking of this thing. A good test of this would be, for instance, really a test would be like we look at, excitations in CFT, in 2+1 dimension, in 1+1 dimensional CFT, in which we excite the vacuum by L-2 by the stress tensors and its descendant, right? And then, of course, there is a precise CFT calculation for the entanglement entropy. In fact, you can, at least even in short distance, you can calculate that thing. And then one can check, actually. In the bulk also, this setup can be done. They've done it for scalars. So far, I think things have been done for scalars. The setup can, then one can see precisely, because the CFT has a well-defined answer for this, actually. About the vacuum, like C/3 log something, plus that extra excited state contribution. There's a well-defined answer, finite answer. So one can actually, I think there is a test for this. I haven't
I have a naive comment. When you compute one loop determinants, in general there are divergences, right? There are intrinsic divergences to all one loop determinants. So I guess you're supposedly separating the divergence and then computing the rest of it. So that divergence might cancel the A/4G divergence.
At least in these setups, the only divergence is the first one, like C/3 log. That is like the vacuum, C/3 log, log of the distance, entanglement over the distance. But then there are finite corrections if there are excited states. So then the rest is finite, actually. Is finite, and that can be checked against. What I think the issue was that the A/4G Newton might have some corrections to Newton's constant, and even the one loop case, the S bulk might have, and somehow they cancel and they become finite. that was the sort of speculation. But there are situations where we can test it, as far as I know. But one has to do it. I think.
To understand that last thing, in IISc there are no gravitons. but there are still these bulks. So the analog of the bulk part presumably is just 0. But the analog of the boundary part is not 0.
Sorry, I didn't understand. I couldn't hear the first sentence.
In ES3, we have no bulk gravitons.
Right, yeah.
So I would imagine that if you had two parts in your entanglement entropy, this bulk term and the boundary term.
Yeah, yeah.
I would imagine that the bulk term in ABS3 is 0. It's some trivial thing.
Yeah.
But
yeah,
the boundary term continues to be non-trivial. Is that true?
Yeah, it could be. Yeah, it could. But yeah, I don't know how it will work out. Yeah, it could be. That should be
but
the way.
You're working with a 4-dimensional theory, right? You're not working in ABS3.
No, this was just an example. I mean, in which this question whether this G Newton thing. I mean, whether the divergence is in. This is different. We are talking about a different setup now. Whether the corrections to G Newton can cancel some corrections in the S bulk. Yeah.
Thanks. That sounds very interesting.
Yeah, it's something which is doable. Impression is it's just that yeah, there are a lot of things to do, and yeah, so it's just yeah. Okay, so yeah, so then yeah, so for the arbitrary spin, though there is no direct calculations like the way we have done, but yeah, but by using the various things we know about partition functions, there is a there is a particular answer for all of these cases: the bulk part, the edge part, and this yeah, and the total basically. So yeah, that sort of brings me to the end actually, and then maybe we can take those questions. Some that I think has been asking. So entanglement properties, yeah, with gauge symmetry with gravitons is interesting, and it's important to understand them because it plays an important role in holography, and as we have just discussed, it's quite crucial in various recent observations now. And so we have, of course, done very simplified setting, but even then it was quite interesting to see how things work out. Yeah. Okay. I think I'll stop, and maybe I think one can, yeah, I can address some of the questions with some that I had. Yeah.
Let's first thank Justin for a very nice talk. Questions?
Yeah, so my question was, in that formula, you had e to the minus t delta plus minus e to the minus t delta minus to start with, right? Then you were substituting the various eigenvalues of delta plus and delta minus and computing the thing. Isn't that correct?
Right. Yeah.
So
That's
the
correct.
delta plus and delta minus are just the Laplacians, right?
Delta, yeah, well, they are the conformal dimension, so to speak. This is de Sitter. Conformal, yeah, so to speak, the conformal weights, yeah, delta plus and delta minus, yeah, like the two weights corresponding to a massless scalar m, yeah, massive scalar m, yeah, just like ADS-CFT, there is a similar formula. I mean, yeah, so
okay, so
it's like the J3. I mean, J3, the value of the J3 for a spin J representation. Yeah.
So they are not eigenvalues of the Laplacian.
Yeah, they're related, I think, by that. Yeah, they're related because, yeah, they're related to that. Just like J into J plus 1 is, yeah.
So in that case, I was just speculating that when you restrict to the DS2 from the 4 dimensions, whether the Laplacian gets restricted to the DS2. And in that case, you should consider the eigenvalues of the restricted Laplacian, and then you would get d minus 3 and whatever you were getting.
Yeah.
That was just
actually, initially we are actually starting with the vector, the full vector, and the vector partition function on the full sphere, or on the de Sitter or the full sphere, a sphere which is related to the de Sitter. Somehow that factorizes like this. I mean, that like decomposes, the partition function decomposes like this. So this observation is sort of new, I think. The fact that there is this, somehow, if you just take the full sphere and evaluate its partition function of the vector on it, it has this nice decomposition. It's a new observation, as far as I know. We're not doing any specific restriction or anything. It's just, we just calculate this partition function, and it naturally has a decomposition like this. Yeah.
I was just speculating whether it can be interpreted in that way.
Okay. No, actually, I don't know whether it's coming. Restriction or of course it can be. I mean, well, it's not. Then it's a vector on SD. I mean, if you because you're starting with a vector Laplacian actually, and then you're reducing it. And okay, there is some scalar part, of course, and I don't know.
But I mean, even if you're considering the vector, finally you compute the Laplacian of the scalar, right?
Yeah, that's because I mean that is of course the entanglement entropy calculation, direct calculation. But this is this is some relation. I mean observation. Like we take the partition function of a vector on S4. Say,
I see. Okay.
Somehow,
Okay. Hi, Justin. Just a quick question. The bulk part of this character on the formula. What are these two terms in the bulk part?
Oh yeah, one is the field itself, and one is the ghost. That's why it's a scalar. View toggle and full screen. Yeah. So there are two terms there also, right? Yeah. But both of them are bulk, but one of them is like a bulk scalar, right? Like b minus 2. Yeah, this is scalar. 0 is meaning scalar. So so that's like because when you calculate the partition function of a vector, you have to gauge fix, and there is a ghost partition function, and that comes. That's due to that. Yeah.
And if I were not looking at U1, but I was looking at just a scalar, then what would I get on the right side?
You don't get any edge. You don't get any edge.
So I would just get the d minus 1 0.
Yeah.
Okay. Thanks.
Justin, I have a quick question. So if I was wondering what would happen if I imagine deforming the shape of the subregion a little bit in the gravity case. So instead of looking at a sphere, if I consider a slightly deformed sphere, maybe in perturbation theory in the shape deformation, do we expect the bulk contribution to actually depend on that? Because I was thinking that because deformations like that are a gauge symmetry, I was thinking maybe the bulk contribution to the entanglement entropy wouldn't depend on that, but maybe the boundary contribution still depends on the shape deformation or the edge contribution. Do you have any comments?
No, I'll have to see. The bulk, shouldn't depend as far as I can. See, I mean, how would one do it also? Because, this calculation of Cassini and all, very coordinate. I mean, like you needed the spherical symmetry to do it. But okay, suppose you deform it slightly away from it, how would one do the bulk calculation?
Well, you could imagine doing the entanglement entropy calculation perturbatively around the background.
One could,
There's some, right. So, but I was wondering whether, right. But I was wondering whether the bulk contribution is sort of independent of the shape deformations, but the edge mode contributions sort of are they do depend on. Anyway, that was my thing. Sorry, Shiraz, I couldn't.
You mean first order in the amplitude deformation in the deformation?
I think so. Yeah. I was just thinking first order because we are thinking about linearized gravity. Yeah. I was thinking first order. Yeah.
I mean, like okay, say we deform the sphere and into some. I don't know. It should matter. I think the edge should matter.
Yeah. I mean, I agree.
Yeah.
Okay. Thank you.
Sorry, one more sort of related question. Can I be heard?
Can you talk again? I mean, I can't hear.
Hi, can you hear me?
Yeah. Now I can hear you.
Okay, I'm really sorry. So it's a question related to Harish, and it's a bit vague. I'm sorry about it. But there is one particular context in which these gravitational bulk entanglement entropies that you also refer to, occur in a well-defined context, namely the dual to the Ryu-Takayama dual to boundary entanglement.
Right, yeah.
Now, in that context, the surfaces that we look at are always sort of either extremal surfaces or some generalization of that, right? The surfaces that extremize this generalized entropy.
Right, yeah.
So I was wondering whether something nice happens in these gravitational entanglement entropy kind of computations when you look at extremal surfaces or some. I was wondering whether you see something special happening for extremal surfaces. Now, I suppose a sphere is not extremal, right? Because it's area.
Yeah, a sphere is not extremal.
Yeah. So I was wondering whether there was something, somehow, sorry to be so vague, but somehow something particularly nice happening in the case that you chose the surface to be extremal.
Yeah. Yeah, it could be. Yeah. I mean, in ADS3, somehow the extremal surfaces are very nice. I mean, yeah, you can map, I mean, given like a vacuum kind of configuration and we have the extremal surface, there is a map to almost like a black hole, you know, and one side is outside the black hole, one side is inside the black hole. And that's how one calculates this bulk entanglement in ADS3. Yeah, I don't know. Yeah, that could be because, I mean, in ADS3, for instance, these extremal surfaces, there is certainly a map from ADS3 with that extremal surface to a black hole, in fact, a BTC black hole, you know, in which the surface is basically the horizon, and outside and inside become outside and inside the horizon.
Right.
Yeah. So there is a very nice feature for that external surface.
Good. Just as a follow-up, I was wondering, could it be that this divergence of Newton's constant and the divergence of the entanglement of entropy, you know, A by 4G plus this, that they cancel only in the cases that the area is
yeah, it could be actually, yeah.
But I have a related point. When you consider a finite gravitational, finite Newton's constant Gn, the entire paradigm kind of changes, because then you have Wilson loops inside the regions which have non-trivial effects on the things at the boundary, which we assumed in the case of the U1 case were absent. Because they can source, because they are non abelian, they can source themselves. If you have non-trivial Wilson loops inside, they can source effects on the boundary. Isn't that right?
Yeah, well, but I mean, you know, at least in this well-defined ADS-CFT context, I mean, the answers are known. I mean, at least in principle, calculable in CFT. No, I mean, one should be able to set up this.
No. Yeah. What I'm saying is one of the fundamental assumptions that you made in the beginning, that in the U1.
Yeah, one has to, of course, extend all these things. I mean, it's not clear how all the things go through, but certainly there are primitive calculations even in ADS3, just using scalars and all how to do.
Yeah, scalars, I agree. Scalars can be done. But as soon as you extend to non-abelian gauge theories and gravity, then
there could be. But I mean, this has a well-defined answer. That's the reason I think there should be a way to do it in the bulk. Yeah, I mean,
also,
go ahead. Yeah.
Yeah. Another point was regarding that minus T delta plus minus T delta minus. In the case of the vector, when you are doing it, so in the case of the scalar, you are saying you don't get the edge mode, right? In the case of the
vector, louder, please.
In the case of the scalar,
you
get the edge contributions, as you said. The green contribution.
Yeah, you don't get to the edge. Yeah, if you just naively write the partition function, you don't have it. Yeah.
Yeah. So could the interpretation be that when you consider the vector, the edge contributions which have to be there in the vector case automatically come in?
Yeah, I mean, yeah. I mean, I'm not like completely related to entanglement entropy to this partition function calculation. I mean, they directly have not, but this observation, yeah. Observation,
yeah.
It's actually, I mean, there is a specific choice of these centers, and somehow some of this partition functions choosing these choices. I mean, that might be a better way. Yeah.
Okay. So just one last way. In the case of Chern-Simon's theory,
yes,
if you try to compute entanglement entropy by cutting something, I believe there's a way of interpreting this as, working in some bigger Hilbert space where you don't impose the Gauss law at the cut.
okay.
Then you get these Wessel-Witten theory modes on the two sides of the cut. And then that gives you sort of the gluing of that gives you the entanglement.
Okay.
Now, this is very vague, but I was wondering whether we might, in ADS3, if we were trying to do gravity in ADS3, whether we might argue as follows. Just like in Chern-Simon's theory, we know gravity in ADS3 effectively has some two-dimensional modes associated with boundaries, which is this the identity block of the Virasa.
Right. Yeah.
So I was wondering whether somehow these boundary modes in ADS3 might be thought of as gluing together two identity blocks of the.
Yeah, it could happen actually. Yeah. One has to, So these kind of questions haven't been investigated as far as, it could happen.
Okay. Thank you.
Yeah. Okay.
Hi, Justin. I had a slightly general question. So there have been these papers by Donnelly and Cassini-Huerta and others where they, and probably also by Sudeep, Ronak, and Sandeep. So they talk about this entanglement entropy for gauge. So they define this entanglement entropy for gauge theory in terms of a Hilbert space, and then they talk about it. So can this be done? So I just wanted to ask, like, whether can something analogous be done for this gravitation case?
We initially thought of like that, but then putting this on the lattice and all, conceptually when we were trying to actually set it up, that was the way we thought, okay, we should go to the extended Hilbert space. But those notions are harder in gravity. But presumably there should be, at least for this linearized theory, one should be able to set up something, actually. Here we just use the fact that, this was like U1 fields, a set of U1 fields. And we just use that. But since they are so closely related to U1, there should be a way of setting it up like that. Yeah.
I see. Because I was asking this because in a certain sense, like in flat space, we know the low energy Fock space structure for this linearized gravitation. So I was just wondering whether this construction could be made.
It'll be good to look at. We started looking at various literature first, because many people try to put a gravity on the lattice and so on. But then finally, like we thought this is a simpler method because we wanted just the log term and a simpler method. It's good to explore that, but
I see.
Justin, can I ask this is probably a very naive question. So, suppose I take Maxwell theory and I fix a gauge, like the Coulomb gauge.
Right.
And then, I can take my A1 and A2, let's say, as the fundamental variables. The wave functions are a function of A1 and A2, and A3 and A0 become dependent on these things and the matter fields. So it's non-local.
You have a matter also.
So let's say I have also matter. So otherwise, the A0 will be 0. So now I can. It just becomes a non-local theory. So instead of a gauge theory, it just becomes a non-local theory. And the problem about splitting writing the total Hilbert space as a tensor product comes because of the non-locality.
Right.
So gauge theory is one case in which non-locality can be handled in the way that you suggest. Okay. So I expect that all kinds of non-localities cannot probably be handled in some clever way. Like this, I was just wondering whether this kind of a method gives us some hint as to how to deal with non-locality. So I was just thinking of one particular example, which is Polyakov gravity, which is R1 over Laplacian R. So which I can write by introducing an auxiliary field. So which is del phi square plus phi r. Okay, so that's the same thing. Now, can I, do the original calculation by sort of thinking of some phi sectors across the cut or something like that? That. So I introduce some auxiliary field to get rid of the non-local nature of the original theory. But I have now some auxiliary fields. And I don't know what I'm saying, but
if it's quadratic, if the theory is finally quadratic, right? Of course, I wanted analytic calculation answers, but if the theory is quadratic, you can in principle put it on the computer, meaning you can discretize it and you can write down, the wave functions and everything, and you can try to evaluate it on the computer. Initially the scalars and all was done by Cassini that way. Even this, what's his name? This Srednicki also.
But the point is I achieved the tensor product factorization by using G mu nu and phi.
G mu nu and phi,
okay. Phi was not there in the original theory.
Okay.
Now, in order to compute the entanglement entropy of the original theory of some subregion A, what am I supposed to do?
Right.
Don't I have to? So this is what.
Yeah.
It's a vague thought.
You have two, now you have two fields, but it's a quadratic theory in the two fields, I suppose.
It's it's del phi square plus phi r, so it's quadratic in phi, and r is something which probably I can linearize as well. So
the question is, when you integrate out the original theory, how much, what are you doing for the phi, right? Then it will.
That's right. What am I doing for the phi? So do I leave the phi as some specified values on the cut, and then later on, I sum over all possible phis? Is that something that because so phi was not there in the original theory. Just a vague thought. It's very vague. So maybe we can discuss.
But the sort of non-locality involved in Polyakov gravity is not the sort of non-locality that you were talking about earlier in the case of gauge fields, when you gauge fix and express the other fields which are auxiliary or which are extraneous in terms of the gauge fixed fields in a non-local fashion. That's a different sort of non-locality, right?
It's a slightly, it's in principle not too distinct. For example, I can bring back the A3 field, as an integration variable. So the theory becomes local, and then essentially, fixing fluxes is a little bit like giving values to the A3 stuff. It's sort of, not very directly related, but it is a bit like that. You bring back locality, but then you have, you have variables which are not there as part of your wave function. Yeah, well, it's all very vague. We can discuss this later, I think. Yeah. Well, thanks, Justin. It was a fantastic talk.
Yeah. Sandeep is not around. I somehow he's not around.
He's in the US.
Oh, okay.
Yeah. Let's thank Justin again.
Yeah, thanks for having me here. It was nice to be there. Sometimes I should come there.
Yeah. Justin, anytime you are able to, we'd be very happy.
Okay.
Yeah, come.